can I make a prototype that can somehow, help me understand how the remora disk works? And also, if I put the disk on a robot, can I mimicking the remoras like a hitchhiking motion when they swim and then attach, from different angles, how they approach the surface and how they catch up with the surface. We also showed one figure in our paper to answer a question is how remora can hitchhike into an object with relatively moving velocity. So it's like this thing is moving and remora goes up. For example, the kingfisher, kingfisher birds, they perch on the trees and near the water surface, and when they see the fish down there, they quickly dive down and catch it up and return to the tree branches and eat the fish. So that's what they do for the whole day. So the whole transition process, or even the whole prey process, takes no more than 3 seconds. So that led me to think, okay, our robots need to transition as fast as possible. So, and how we can do this? So this is our purpose. We want to make a robot that can transit as fast as possible.
In this podcast, I'm sharing my passion and curiosity for soft robotics, where we share inspiring stories about the work we do and how we can push the limit. I am Mara Dwiney, and this is Soft Robotics Podcast. Support for this show comes from Science Robotics Journal. I really find Science Robotics to be a great resource for reliable and tangible research where we can really push the limit of the science we do in robotics. Great way to stay up to date with the published article is checking out the released monthly issue. All the links will be included in each episode description. We will also happen to have a regular conversation on the most published science robotic articles, where also you can contribute with your question and thoughts about the research. Thanks Science Robotics for sponsoring Soft Robotics Podcast.
I was asking you about maybe the story behind, the glimpse behind the Aerial-aquatic robot. Can you tell us briefly the idea behind this paper before deep dive in the design consideration for this robot?
Yeah. So actually, this robot is inspired by two animals. One animal is remora suckerfish. The remora suckerfish, our group started to do this work almost 10 years ago. This remora suckerfish can hitchhiking on many marine large animals like the whales, the dolphin, the sharks, and sea turtles by using its suction disc on its dorsal side. And this suction disc is very unique. It's evolutionarily modified from its first dorsal fin into a very particular shape. And this disc can provide very powerful suction on water, and also they can have adaptive adhesion to a lot of surfaces with different roughness and with different surface properties. So this feature intrigued us to understand what is its morphological functions. So our group started investigating the structure 10 years ago, as I mentioned. And then we published the first paper actually in 2017, also on Science Robotics, just by introducing its fundamental mechanism, how the disk works. We found that the disk has a disk lip as surrounding to creating the seal, and also inside they have rows of lamellae with microstructure on it, and these rows can be actuated by muscles so that they can control its microstructure engaging a surface or not, so that they can control their friction along the shear direction. So we found this mechanism, but at that time we make a very simple robot in 2017 with tethers, with battery outside, and also the robot cannot move well. They can just move up and down by sticking to a flat surface. So after 17, our group is thinking, okay, so I think we should improve the disk so that the disk can adhere to more complex surfaces. And also we want to improve the agility of the robots. So this is our two initial thoughts in 2017 after publishing that paper. So we after 2017, we keep looking at the animals. We found the remora as a disc is and has another unique feature that the remora disc, they can only use part of it as a disc, like half of the disc or just one third of a disc to stick to a surface. Or they can stick to a surface with many holes or porous surface. So this is not this cannot be achieved by traditional suction cup if you think about its fundamental principle. So we want to figure out why this happened or how this happened. So we're using a lot of biological observing tools like micro CT, and also we use a surface like observation technologies. And also we use like a DMA or other scanning electron microscopy to look at its structure into great details. We found that the disk have a very special structure which allow the disk to have redundant adhesion. So we call this redundant adhesion because it can stick to the surface just using part of it. So, and after understanding this, we make a biomimetic disk, and we want to find a add into a robot. So this leads to the second contribution of this paper. So the disk is one contribution, and the second contribution is a robot. The initial thoughts we think of adding the disk to our Aerial-aquatic robot that can cross air-water boundaries. Okay, so my student talking about this. If we make an underwater robot that can stick underwater, you cannot do better than animals. So is there any point that we can, beat the nature in some sense? So that's our initial thoughts is, okay, let's find a robot that can do better than the animals. That is a remora suckerfish. Is there anything we can do? So let's try to make the robots not only can stick underwater and also swim underwater, but also they can fly into the sky by crossing the air-water boundary, and also using the same disk that can stick in the air, in the surface in the air. So there's no animals can do this. So in such a way, we can convince ourselves in saying that, okay, at this point, there's no animal can stick both in air and water, and also by crossing the air-water boundary. So we can beat the nature in some point. So I think that's how we get inspired, and the path leading to our our robot design. Yeah.
Very interesting, very interesting. Maybe quick question here, Lee, about the adhesion. Maybe the first part about inspiration from this fish, for example, and the adhesion. When we look to the gecko, for example, some people work and inspiration from the gecko. What does differentiate, maybe that's the basic question, the adhesion? Is it because of the medium here, water, and here, wall and surfaces? Just the basic part, the adhesion. What's the difference, like gecko and the remora fish here? What's different
Yeah.
for adhesion?
Okay, so gecko adhesion is by van der Waals forces. That's molecular interaction. So it's mainly can work in the air. So when it's merging on water, this kind of mechanism doesn't work well. So remora's adhesion is very different. So its principle is by using pressure differential and the mechanical interlocking by microstructures. These two coupled mechanism together. That's a principle of the remora. So it can, and also it's flexible, so that it can adapt to rough surface and creating the pressure differential. And at the same time, its microstructure can engage. We call it mechanical interlocking with the surface local asperity. So that's her principle of remora, which is different with geckos.
You mentioned at the beginning you focus now on embodied intelligence, and maybe I want to ask you again here about the architecture, because I think the main thing here about the morphology of the remora fish here, inspiration, the basic part of the morphology. How do you see the interplay between the material and architecture or the morphology when it comes to fish itself? And then when you try to surpass what you have already as a feature now, going from the air, from water to air, and combining all this together, the material and morphology. How do you see all this together play in the design, the material and architecture or morphology? How these two play together? Yeah.
I think this is a very good question. So actually, I think material is really important because first, a remora disk is soft, not only on the like the surface, like the skin that interacting with the surface, they has to be soft or soft enough so that they can adaptive to self-adaptive to rough surface, and they can create a seal better. And at the same time, the overall disk is also soft. It's not stick like a rigid suction cup. It can bend, so that think about the remora. They can stick to like the tunas. The tuna's body is not flat. It's curved surface by both x and y axis or axial or lateral directions along. So they have to bend this disk to fit the host surface. So that's, I think that requires the soft materials. To implement in the flexural stiffness of the disc, we use like silicone rubbers and many other soft material to realize this. But I believe that in the future we can use smarter materials that can tune the stiffness so that it can adapt to more surface as well. And also there's another structure, adaptive structure, which is a propeller of the aerial-aquatic robot. The propeller is self-folding propeller, so it can unfold in the air. So they shape like an aerial propeller. When it's merging on water, it will become a folding to a hydrofoil, so its diameter will shrink like this. So in this way, it can work efficiently in both on water and in air. And what is special is, if you see our paper, we show during the transition, this kind of self-spanning or self-unfolding from the air, from on water to air, will increase the speed of the transition to like 60%. So I think that's very interesting because this self-folding propeller can not only increase the efficiency when the robot is working on water or in the air, but also can increase the speed of the transition. So I think that's that's another morphology thing we incorporating into the robot.
Mm-hmm. When you mentioned the design surpass what we saw already in evolution, for example, what you said, what the first step in the design thinking about? Yeah, you have to consider that if you try to push beyond what we have as an inspiration, bio-inspired, but we have to push that to a certain level. What are the process to the design thinking, or the most significant part? That something we have to figure out if we want to push beyond what we have in evolution, for example, in this paper, for example.
Mm-hmm. Yeah, so I think the design thinking is every lab have their own philosophy of design thinking. Some labs may aim for like a higher performance, higher metrics, so they have their design thinking. For our lab, it's the first principle is trying to answer the question in biomechanics. So we try to make the prototype as similar or as biological relevant as animals do. So by creating this kind of disc or any other robot or biomimetic robots, we hope to use the robot or the prototype to answer some of the biomechanics questions we're willing to answer. So I think that's our design thinking is, okay, can I make a prototype that can somehow, help me understand how the remora disk works? And also, if I put the disk on a robot, can I mimicking the remorse like a hitchhiking motion when they swim and then attach, from different angles, how they approach the surface and how they catch up with the surface. We also showed one figure in our paper to answer a question is how remora can hitchhike into an object with relatively moving velocity. So it's like this thing is moving and remora goes up. And according to these robotic experiments, we found that, okay, remora is first by approaching, and there is attached the following stage, which is or sliding stage before the attach the following stage. So this cannot be reviewed without the robotic experiments. So we use the robotic as tools to answer the scientific question, and that's our design thinking.
Maybe in the coupling on this, the aerial and aquatic, for example, here, is there something maybe very challenging in the design, maybe in counterintuitive or trade-offs sometimes? Is there something you can share or very exciting or be counterintuitive or hard to just to understand the coupling between transition from water to air? There is any parts you can share about maybe counterintuitive or not easy to understand or was challenging before being published in the paper?
Okay, so I think the first thing for this kind of robots is not too many people can have done aerial aquatic robots. There are some papers, but in our paper we just want to make the transition faster. Some of the papers use like a buoyancy device to let the robot first float into the surface and then the engine start rolling and then pull it up out of water. The whole process take like over 20 seconds or even 1 minute or even longer. So I think that's not animals do. Animals just transition very quickly. For example, the kingfisher, kingfisher birds, they perch on the trees and near the water surface, and when they see the fish down there, they quickly dive down and catch it up and return to the tree branches and eat the fish. So that's what they do for the whole day. So the whole transition process or even the whole prey process takes no more than 3 seconds. So that led me to think, okay, our robots need to transition as fast as possible. So, and how we can do this? So this is our purpose. We want to make a robot that can transit as fast as possible. If we look at the video, we want to make the robot look like a kingfisher. So that's our initial situation. And then, our design is trying to make the robot move between the air-water surface reversibly and as fast as possible. So that's the challenge is if you want to realize this, you have to make everything like waterproof engineering question to be well solved because we want to test it multiple times. So there's an in and out of water for about 30 times and then it doesn't break everything. So that's a challenge. You hope to get some very good data, and then you have to make the robot as robust as possible.
Maybe can you push more, go and explain more about the transition? If there is any other way you thought about, since you already mentioned the traditional approaches, maybe 20 seconds, but do you have any other idea that could make it faster? I don't know if you can explain more in detail this part and maybe thoughts or idea you thought about this transition and maybe failed or something. If you can share these, the possibilities beyond what were in the paper for fast transition.
I can share some of the knowledge, but although I haven't tried it, but we read many other articles, very good studies. For example, somebody using like a explosion way to propel the robot out of water. So the speed, the transition or the propellant speed is really high because the explosion happens and then it jump out of water in just less than half a second or something. But it's not reversible. Once the explosion, and then if you want to make it re-exploded, it have to take a long time. So after looking at all the possible solutions, we still choose a propeller solution because we think this is still the most efficient, robust, and stable way to make the robots transition well, because you can make it a reversibly transition. While other robots, although their transition mechanism could be quite new, using chemical ways or using some other material way to overcome the water surface tension. But the thing is, it's just one time. When you jump out, if you want to re-jump, that's not possible. So I think our approach is you can reversibly transition at a very fast, high frequencies.
Great. Maybe I'll ask you, Lee, in the bio-inspired maybe design field, if there's something you disagree with, maybe you maybe highlight the part of the transition, but in generally speaking, do you think, yeah, does it make sense to you, or the approach is maybe that's maybe not the right way, or you have disagreement? Do you have any critical source or disagreement in general for design in bio-inspired field? Different views or different opinions. Yeah.
Yeah, so I think I want to share my views on the bio-inspired. For example, our robot, in this paper, I would say the disk is biomimetic. So it's not only bio-inspired. We just try to replicate the morphological features of the remora disk as much as possible. So I think we have a biomimetic disk. While I think the Aerial-aquatic robot is not that bio-inspired, because the animals are using for example, the flapping wings or some other ways to get out of water, or using like the fish jump out of water by using tail flapping. But we did not use that. We did not use a robot fish to jump out of water. We did not use a bird to leap out of water. We use a traditional propeller. That's because I think it's more stable and more robust way to get out of water. So according to the two things on the robot is, I think my views to bio-inspire is use biomimetic structure. If you hope to answer some of the scientific questions, you can build a biomimetic prototypes. But if you want to reach a really high engineering performance, I think you should look at balance the bio-inspired and traditional engineering ways together. For example, the self-folding propeller is some sort of in the middle of of the foldable wings and traditional propellers. So if you search the trade-off points is a self-folding propellers. So they can still have some like a bio-inspired ideas, but it's still engineering device. So that's my point.
Maybe also point about redundancy, because was mentioned, and how do you see the redundancy here, the transition from the air to, for example, water to air, and also if there's failure in the actuation, how do you see this process going on? Is it something, I don't know, since we can put it intelligent, is it something in morphology like physical intelligence only, or control? Yeah.
Yeah. So first, to answer your first question about redundancy, we use redundancy in this paper to describe the disk, not the whole robot, or describe the diffusion, not the transition. So, but the advantage of redundancy is in many nature's surface, they're incomplete. They only have a very narrow strip. They are not like a perfect, full, smooth, flat surface. They're pretty challenging. They're rough. They're slippery. So how did the remora can overcome these challenges? Because their disk have the redundant features. By just using part of the disk, you can still sticking on it. So, but I think the redundancy not only referred to remoras, but also some other. I think the gecko have some sort of redundancy as well, because if the gecko can use part of his tones to stick on the surface, because the geckos have a lot of hairs on it. So the redundancy can provide the robot with some sort of we call embodied intelligence, because it can reduce cost of the control. If you want to make a robot with a traditional suction pad to stick on some surface, like an incomplete surface, you need a perfect control. You need perfect vision and then feedback control method algorithms. But if you have the disk, which allows you to stick by using just part of it, and then your control is simplified. So this is some sort of way it can provide you a mechanical device that can reduce the control cost, which is good. So, and that's what my answer to your redundancy. And then you talked about the actuation, right? Yeah. So the actuation of the current robots is not that. I would say it's still we use a hydraulic way to actuating the disc, and also we use a traditional brushless motor to actuating the rotors. So it's not too special. But we choose the components, property components that can reduce, not spend too much power, and that are lightweight and waterproof. Yeah.
Great. So
Not
since
too
we're close to
special
the
on the
end,
actuation.
yeah. So since we're closing, I have a few questions for you. Maybe the first thing, what maybe still missing? You mentioned that this robot's really surpass what we have in evolution, but when you try to think about the question in your mind, yeah, still missing, or if you can share the thoughts in your mind about the end goal, or maybe the point that you think to push again the design. Do you have any kind of thoughts in mind, or still missing in the design in general here? Maybe in the paper in general, in the bio-inspired or biomicro field, what's missing is there? Or maybe question you mind, you think still not really considered. Yeah, in this paper we try to push something, but maybe you wish for more. Yeah.
Yeah. I think this paper is still have several limitations, not just one. So, but if I at least the one of the most thing we want to do is for the next is add some sensory feedback. So right now it's still tele-operated by humans. So we have operator control the robot. So, but I think the robot, if you think about the future application, possibly, you can tag in the whales. So that's something I really want to do is like, if you use the robot to help to understand some of the ecological questions, like tracking the whales and understand how the whale populations, to understand the whale population or how much the whale eats and how much they pump out, those questions need the drills. And sometimes not only drills, but the drills that can dive down into the water and even attach to the whales to get more data of the animals. So to realize this long-term goal, you need add sensory feedback. You need add cameras to it, by which, and also algorithm which allows you to recognize objects or some animals across air-water boundary, which means that you can recognize the whales when the airplane and when the drone is in the air, so they can dive down into the water to tag the whales in some sort of sense. So that's one thing I think the robots needs to add. And also I think the current robot cannot dive very deep. They can only dive to depths of 2 meters autonomously. It can stick to a swimming host, dive down to deeper, but it's not self-actuated. So we hope that the robot can reach a deeper depth.
Mm-hmm. Maybe if you question the first thing about the functionality, what other functionality you wish maybe integrated maybe in the material in this robot, if you imagine, or the morphology or architecture in the design? Is there certain functionality you think that I wish I can add this functionality?
Of the functionality is you mean the research from the research point of view or from the application point of view? So
Maybe both. If there's
okay,
something,
so
maybe yeah.
yeah, so I think the transition is actually I talked to several guys, research scientists. They are pretty interested in reading air water transition, but not only just by using like propeller designs. They can use some other materials, special materials like even origami or some other structures that can be one shape on water and be another shape in the air, autonomously without any power input. They can, change the shape, and also can this shape be helpful to the transition process? So that's using, in one sentence, is using smart materials or structure to realize the transition or boost the transition process. That's one research topic that people are interested in. And I think that for future applications, we need to solve the problems more from the control side. That means, how do you make the robot more autonomously? When the robot fly out of your sight, it has to be working in some at least a semi-autonomous way. Can this robot make a transition in an autonomous manner? This is more from a system control question. Yeah.
Mm-hmm. Maybe the last question: if there's any other animal in animal kingdom, maybe inspiring in the design, and if there's something you would love to change in the design, maybe in this paper, if there's something you think maybe in the future iteration to change certain aspects of the design.
Well, that's a very good question. I think the body of the robot can be altered to many other shapes, not look like a cutter rotor. This is a very classic engineering shape. Like many birds, they have perfect design of the wing and the body shape when it's dive down into the water. So they can make the drag very low when entering water to reduce the fluid drag, and also they can quickly, spanning the wings out to return to the flapping states, and all the water can be quickly flashed off. So this requires new mechanisms and new materials to be involved in the future studies. I think there are some studies like Professor Milko Kovac, which is also the co-author of this paper, who has studied some like fixed wings, how the fixed wings can dive into water quickly. So that's in some sense like a morphology things. But I think we need smart material side also getting involved to make a faster or high performance transition and more bio-inspired.
Wonderful. I don't know if I have any final words like say, or maybe other questions left maybe to people ponder about and about the paper, or maybe in this field in general. Other final words like say here or thoughts, yeah.
Oh, thank you. So I would say first, biomimetics is very interesting field. So there are unlimited questions remain to be answered in the area of biomechanics, while the robot is a very powerful tools to answer those questions. So I think that's why we do biomimetic robots. I hope people are getting more interested in this field. And also, I think the aerial-aquatic transition has just started. This field is, I think they have promising future applications. I hope that in the future we have more materials, more smart structures, and more control people to get involved so that we can make the, aerial-aquatic transition, this robot better. Yeah.
Mm-hmm. Again, thanks so much, Lee. It was really inspiring listening to you, and congratulations again for the paper. I think it's really
Thank you very
interesting.
much, Marva.